So, as promised, we've talked about periodic trends and atomic size and ionization energy, and we're going to try to do electron affinity and ion size today. Okay. So, electron affinity, like the words say, is how much something, an atom, has an affinity for electrons. How much it's trying to, it's willing to gain, or how much it's willing to allow electrons to come in close to it. So the amount of energy released when an atom is added to an oh shoot, I blew it again. When an atom is added, no. When an electron is added to an atom. Fortunately, I only got one wrong. I did the whole definition and got one word wrong the second time around. So who knows what that means? It just means that there's stuff going on here. Okay, so some atoms are much more willing to accept electrons than others, and there's a good chance that by now you've seen a lot of those atoms that'll do it. And so when we look at the photoelectron spectroscopy data, and when we look at the periodic table, you're going to know intuitively what some of those atoms are. So let's take a quick look at a periodic table for just a second here. So one of the things that I know, Kevin, and I think you know, and I think many of our students will now be starting to recognize, is that there are elements over here on the right-hand side of the periodic table, the non-metals. And we've seen those with negative charges as ions. So we've seen F-, we've seen Cl-, we've seen Br-, bromide, chloride, fluoride, we've seen oxide and sulfide. And that says, okay, we know that those elements form negatively charged ions. And so that says that as a general rule of thumb, we're going to see those elements are willing to add electrons to their orbitals. And we also know that over on the other side of the periodic table, things like lithium and beryllium and sodium and magnesium and calcium and potassium, we've seen those with positively charged ions. We've never seen them with negatively charged ions. So the chances of these metals gaining electrons is very, very slight. So at first pass, that should tell us, hey, elements over here on the right-hand side, the non-metals, are much more willing to accept electrons. Metals on the left-hand side are really unlikely to accept electrons. And so that should tell us a little bit that elements like fluorine, chlorine, bromine, sulfur, oxygen have high electron affinity, and that elements like sodium and magnesium have low electron affinity. So far, so good?
Yeah, that makes sense.
Okay, so now what we're going to do is we're going to look at some numerical values and try to get an understanding of what those numerical values mean in terms of what's going on with the atoms itself. Okay, so if we look on this chart, on this graph, here are fluorine and chlorine down at the bottom. Hold on, didn't we just say that they had high electron affinity? Well, they do have high electron affinity. It means that they're in the range of releasing 300 kilojoules per mole when the electrons come down into their orbitals. So they're at the bottom of this graph, but they have high electron affinity, okay? And then if we look a little bit up in the middle range, here is lithium and hydrogen and sodium. Okay, apparently their electron affinity values, apparently you can get an electron into them sometimes, right? And you can get a little bit of energy out, but it's on the order of 50, 60 kilojoules per mole. A lot, their desire to have electrons is a lot smaller than fluorine and chlorine. Okay?
Yeah.
Now, let's go back to the periodic table again for a second. that's the nonmetals that form negative ions. It's the metals that form positive ions. And then we've got these noble gases, which almost never are we ever going to see those in forming a compound of some sort. We never see them with positive charges or negative charges. And so that tells us that they're not taking electrons either. Right? We know that that's reasonable, that's the case. Here is and here across the top, okay, here's helium, here's neon, here's argon, and they actually have slightly positive electron affinity values, which means that there's no way in HE double hockey stick that they are getting electrons added to them. And so they have very, very low electron affinity values because they don't really want to take electrons. And so they're up here at the top of this chart. How am I doing?
So basically, the lower on the graph, the higher the atom's electron affinity is. And
Correct.
the higher up you are, and an element is on the graph, the less electron affinity that atom has.
Right, right. And so we can, there are a couple of things that we can do to rationalize that a little bit if we want to. So yes, if it's lower down on this graph, it has a higher numerical value of the amount of energy released. If it's higher up on this graph, the amount of energy released is either very, very small, or actually it's the negative of the negative amount, right? Because it's a positive amount. So you just can't get them in. You basically cannot get electrons in there, okay? What I want to do is I want to go and see if we can rationalize this in terms of some of the atomic structure.
Of course.
Okay, so let me stop that share. Let me bring up the photoelectron spectroscopy. Okay, so what do we know? We know that fluorine right here is an element that pretty readily accepts electrons. And so if we look up, we see fluorine has 5 electrons in its 2p. It only needs 1 more electron to get to filling up the 2p and having a complete octet. In the case of something like boron or beryllium, they're going to have to add a lot of electrons to fill up complete octets. If we look at chlorine, chlorine has 5 electrons in the 3p. It only needs 1 more electron to fill up the 3p, and so to complete its octet. And so there is something special about these elements, these nonmetals, that filling up octets is an advantage for electron affinity. And so the nonmetals have a long way to go to fill up octets. The metals have a long way to go filling up octets. The nonmetals are almost there. And so we see fluorine, oxygen with favorable electron affinity values, and we see the metals with unfavorable electron affinity values. Okay?
Okay.
So if we go back to the chart, here we see elements on the right-hand side of the periodic table. They only need 1 more electron to fill up their orbitals. We can see that elements on the left-hand side of the periodic table have unfavorable electron affinity values. And so going from left to right, let's look at the periodic table again. Going from left to right across a period of the periodic table, the electron affinity values are going to increase as a general rule of thumb. That we've got metals with unfavorable low electron affinity values, and we've got non-metals with much more favorable higher electron affinity values. Okay, let's go in the other direction for a second. So as you go down a group of the periodic table, the general trend is that for the electron affinity decreases going down a group of the periodic table. So that means that the desire to accept electrons gets worse. Here's a way that we can look at that. Here are some electron affinity values, and you can see that as we go down the periodic table in like group number 1, the values are getting smaller. As we go down a group over on the right-hand side of the periodic table, the values are getting smaller as well. Okay, and that's as it says, it's because the electron can't, as you move down the group, the distance between the valence shells and the nucleus increases, and so it's the attraction of adding the electron to that orbit, to that atom, gets smaller. Okay, and so as a result, the electron affinity is smaller. Okay, those are the general trends for electron affinity as you go across periods of the periodic table and as you go down groups of the periodic table. There are some exceptions that the text will outline for you, and if somebody asks me a question about that, we can work on those, but that's generally how it goes for electron affinity. Do you want to ask a question or make another comment on any of that, Kevin?
Just, it's confusing with the graph and the numbers, especially with the negative numbers, but like we kept on saying, the lower an atom is on that electron affinity graph with the energy values, the more electron affinity that atom has, and then vice versa. So
right.
Just try not to get confused with that. And sometimes it's easier to kind of forget about that numerical value data with the negative signs and just try to think about it through energy level diagrams and the PES graph.
Yeah, for me, that's the only way that I can do it, is I have to start from the place of thinking that I know which elements form negative ions and which ones don't. and so if I can remind myself, okay, fluoride, bromide, those ones form negative ions. It must be possible to put electrons in there, so they must have the highest electron affinity. Then I can go and say, okay, if they have the highest electron affinity and they've got this big negative number, that must mean high electron affinity. So that's the only way that I can do it. And even as I'm talking about it now, I have to be really careful not to confuse myself with the negative signs and the double negatives and the negative and the word negative in a sentence that also has 2 or 3 other negatives in it, right? So it's a challenge, that one.
Yeah.
So shall we move on to something else?
Yes, let's do that.
Okay. We promised electron affinity today and ion size, right? And ion size is just how big the ions are that are formed from various atoms. So there's that one conceptually is a lot easier to understand. We know that if something gains an electron, it becomes negatively charged, so it's a negatively charged ion. If it loses an electron, it becomes positively charged, and so it's a positively charged ion. And if we look at the graph of trends in ion size, so if we look at this graph, we can see that there's a faded dotted line showing the size of the neutral atom, and then the size of what happens to the ion after it either has lost or gained electrons. And so up here on the left-hand side, you can see that there is a lithium with a little faded line just slightly outside of the size of the lithium ion, right? So there's a lithium atom, it loses an electron and it becomes smaller. Here's a sodium atom, it loses an electron and it's smaller. Here's a potassium atom. It loses an electron and it becomes smaller. So for those atoms that lose electrons, if we go to the photoelectron spectroscopy graph. So with lithium, lithium has electrons in the 1s and the 2s. When it forms a lithium ion, the 2s is gone, and so the resulting atom, or the resulting ion, is smaller. With sodium, it's got 1s, 2s, 2p, 3s. It loses this 3s electron, and so it only has the 2p and the 2s left, and so it's smaller. Here's the atom size, here's the ion size. The atom size, the ion size, right? And so it's smaller. And if we look at potassium, potassium has 1s, 2s, 2p, 3s, 3p, 4s. But when it forms a potassium ion, it loses this 4s electron, and as a result, it's smaller. Okay, now let's go to the graph. So here we're looking at this graph from this table from the text. Here is lithium ion smaller than lithium because it's lost its 2s electron. Here is a sodium ion smaller than a sodium atom because it's lost its 3s electron. But the ions themselves get bigger as you go down the group because the electron, it still has remaining electrons that are in larger subshells below the valence electrons, or the valence positions. How's that?
Yes, that makes sense, because potassium still would have 3p, and then rubidium would have 4p, and so those atoms, those ions, still have a lot more electrons.
Right, right. Okay, so that's the ion size going down a group on the right-hand side. On the left-hand side. On the right-hand side of the periodic table, the nonmetals, you can see that the ions are actually a little bit bigger than the atoms. And so we've, again, as we go down the group of the periodic table, the ions get bigger, but the ions themselves are bigger than the atoms from which they were formed. And that can be explained by saying, hey, if I throw an extra electron into any one of these orbitals, I'm going to have more electron-electron repulsions, and so the ions are going to be a little bit bigger because they'll be pushed away from each other, pushed away from the nucleus a little bit more.
Yeah.
And so again, so if we see in the photoelectron spectroscopy data, so here we have fluorine. It's got 5 electrons currently. We add a 6th electron. That's going to increase the electron-electron repulsions, and so it's going to be a little bit bigger. Chlorine, it's got 5 electrons in the 3p. We're going to add that 6th electron to make chloride. It's going to have a slightly greater repulsions, and so it's going to be a little bit larger than the atom from which it came. So if we go back to the chart from the text again, going down a group on both the metals and the non-metals, the ion sizes increased, and going across a row, the metals get smaller, the ions get smaller as we go across, and then we get a big jump once we get to the nonmetals, and then they start to get smaller again. So fluoride -1, oxide -2, and nitride -3 all have the same number of electrons. They both have, all 3 of those have a complete octet, right? The p orbitals are filled. In fluorine's case, it just needed 1 electron. In oxygen case, it needed 2 electrons, and in nitrogen case, it needed 3 electrons. So here is fluorine, oxygen, and nitrogen. If I look up at fluorine, 1 electron makes a fluoride. If I look at oxygen, 2 electrons make oxide. If I look at nitrogen, 3 electrons make nitride. So F minus, O2 minus, N3 minus. So 1, 2, 3 means that they all have exactly the 6 electrons. They have a complete octet out here in the 2p orbitals. So far, so good?
Yes.
So if they all have the exact same number of electrons, but down here in my nitrogen, I've got 7 protons. In oxygen, I've got 8 protons. And in fluorine, I've got 9 protons. So I've got 9 protons attracting that octet, or I've got 8 electrons attracting an octet, or I've got 7 electrons attracting an octet. They're not all going to attract those electrons equally. The ones that have more protons are going to attract electrons more strongly. So if I've got a stronger attraction between my fluorine nucleus and these electrons out here, it's going to pull them in. Nitrogen doesn't have such a have as many protons, and so it's not able to pull them in as far. So that means my nitride is going to be bigger than my fluoride. Let's go look at the graph. Here is nitride, distinctly bigger than fluoride. Nitrogen has 7 electrons in its proton, nitrogen has 7 electrons in its nucleus, attracting that octet of electrons. Over here in fluorine, we've got 9 protons attracting that same octet. 9 protons can pull in electrons more strongly, more closely than 7 electrons can. And so as a result, fluoride is smaller than nitride. So as we go from nitride to oxide to fluoride, the ions get smaller. Likewise, sulfur is slightly bigger, sulfide is slightly bigger than chloride because there's an extra proton pulling those electrons in. And the same with selenide and bromide. So thinking about what goes on in the nucleus and the number of protons will help you understand what's going on with the ion size as well. What do you think, Kevin?
So with ion size, with the metals, as you go further to the right in a row, the ion size decreases, but with the metals, the ion size also decreases. It's just distinguishing that metals get the ion gets smaller than the original atom, but with the non-metals, the ions are getting bigger than the original atom, which is a little tricky.
Yeah. None of this is trivial in the sense that there's a lot of intellectual, mental manipulation that's going on to try to understand what's happening with these particles, or these atoms that are so small we can't see anyway. They're so small we can't touch them, right? I mean, it's a big mental challenge, and this is one of the places in this course where your ability, my ability to wrap our heads around the non-visible concepts can be really challenging.
Mm-hmm.
So good luck.
Yeah, just keep up with the homework, ask questions. Good luck.
Yeah. And we're here to help. Hopefully we're more of a help than a hindrance. That's the plan anyway.
Yeah. All right, then. I think that's all.
All right. Okay, thanks, Kevin.
Thank you, Dr. Hunter.